Okay, so we started talking about our subject matter. Also, we talked about the syllabus, and we also started talking about subject matter, watched some videos about, I mean, the videos were basically related to the first part of the class, right? So the compressible flow subject, so fast, high-speed aerodynamics, I can say. And so that's what we're going to continue discussing. So basically, we started first discussing this equation of state, we call it, right? P equals rho times R times T, which is also known as the ideal gas relation or perfect. Basically, it's valid for basically what we call a perfect gas, where intermolecular forces can be or are negligible, let's say. So these are the parameters in this equation are, of course, what we call macro scale properties: pressure, density, temperature, and this relation through this constant, gas constant, is the equation of state. For air, this has a value of 287 joules per kilogram Kelvin. And for if it's a different gas, it will be different, because this gas constant in reality depends on the molecular weight of the gas. So there is in reality a universal gas constant. So when you divide that with the molecular weight, you end up with the specific gas constant for that, for the gas constant for a specific gas. And this number is 287 for air. Now, we will continue from this point. Of course, these high-speed aerodynamics, as I kind of tried to introduce you to back yesterday, basically, is I said fluid mechanics is, of course, important. Sorry, but thermodynamics is also very important, because the thing is, also, if you remember from some of our videos, these energy interactions are very important if you start flying at very fast speeds or very high Mach numbers, let's say. So therefore, the concept of energy and, therefore the concepts of thermodynamics, like first law of thermodynamics, second law of thermodynamics, now have to be integrated into the picture. So before we go there, so let's remember some of the fundamental topics related to energy. And the first thing that, sorry, let me switch to the black pen. The first thing that we will remember, I think I'm quite sure that you covered this in great detail in thermodynamics, is the concept of internal energy and enthalpy. Okay, enthalpy. Let me change the thickness a little bit. Okay, internal energy and enthalpy. So, of course, the thing is, when we are dealing with gases, and in air, as we talked yesterday, we have nitrogen and oxygen, for example. So if we have, let's say, an O2 molecule, so these are connected together, let's say this is representing oxygen molecule. And we have, of course, nitrogen as well, N2. The thing is, in the molecular world, in the world of molecules, of course, first of all, we are talking about a fluid. So these molecules are freely moving around. So they have basically what we call like a translational energy. This kind of corresponds to like the kinetic energy in the macro scale. So because of their, they do have a velocity, they do move around, so they do have what we call a translational energy. And in addition to this, in addition to this, these molecules have, rotate around certain axes due to basically different reasons. So they do not only linear motion, so translation, but also they do have rotational motion. So a rotational energy is relevant as well. In addition to this, the bonds between atoms in molecules, they are not, due to different atomic, let's say, processes, these molecules also vibrate without going into any further detail. So they do, in addition to translational and rotational energies, they do have a vibrational energy as well, okay? And of course, in the atomic sense, in every atom, there are electrons that are moving around the nucleus. So there are also, there's an energy level involved with the electron movement. And we can call it the electronic energy, okay? Because of the fact that electrons are moving. Now, of course, these are all in the molecular sense. The thing is, these translational, rotational, vibrational, electronic energy levels that we observe in the molecular sense, how do we reflect this into the macro world, right? Into the actual, like, fluid mechanics problem or aerodynamics problem. Thermodynamically, all these are reflected as a macro scale parameter we call internal energy. Internal energy. Or sometimes we also talk about internal energy per unit mass. So this is known as the specific internal energy. Specific internal energy. So therefore, it's basically kind of an average representation of all these molecular level energy combinations, energy summations, let's say. The internal energy we describe in thermodynamics, and sometimes we use in some textbooks, they use the letter U to indicate this. In some ones, they use the letters small case e to indicate internal energy. It's a global parameter, and it is basically an indicator, like a macro indicator of all these molecular level energy types, I can say, okay? So this, in this class, we will go, I will go with the small case letter E to represent what we know as internal energy in thermodynamics. Now, a related quantity that is a related quantity to internal energy is known as enthalpy. Also very much of importance. We will see later in coming weeks that very much important parameter for high-speed aerodynamics. Enthalpy, generally we designated small case letter H, and H and E are related. The equation is the enthalpy is equal to internal energy plus P, pressure, times specific volume. Okay, small case V. By the way, I forgot to mention, if I go back to our equation of state, P equals rho RT, this equation can also be written as this: P times specific volume is equal to R times T. Here, the definition of specific volume is that it's equal to 1 over density, okay? So here V is specific volume of a substance. So its unit, as you can see from here, I mean, the unit of rho is kilograms per cubic meter. So therefore, a unit of specific volume is meter cube per kilogram. So it's basically, if you take 1 kilogram of a substance, a gas, air, any gas or any fluid in that matter, for that matter, as long as, I mean, any fluid, then if you take 1 kilogram of it, how much space does it actually occupy, its volume in cubic meters? So the specific volume is meter cube per kilogram. So that same V is also here. It appears in this enthalpy equation. It's actually thermodynamically how these are related. And we can also, of course, replace this. Instead of P, instead of specific volume, I can write 1 over rho. So this becomes equal to E plus P over rho, specific, enthalpy. So these two quantities, both H and E, so both enthalpy and internal energy, these are actually not constant values, okay, for a flowing gas, for an aerodynamics problem, let's say. These change with temperature. In general, both of them, H, enthalpy is a function of the temperature of the gas, and internal energy is also a function of the temperature of the gas, okay? So the thing is, right now we don't know that function. We just know these are representing, I mean, conceptually, both E and therefore H, they are representing the molecular level motion, I can say, and they change, their numerical values that they get, they change with temperature. And temperature is also related to, as you might remember maybe from thermodynamics, temperature is also an indicator of molecular activity, okay? Molecular kinetic energies and everything. So high temperature, if you have, let's say, two types of gas, one at low temperature, one at high temperature, you can directly say, let's say in a container, one container has a cold gas and another container has a hot gas. You can immediately say the molecular motion, molecules are moving faster in the high temperature gas. So this temperature is like a macro scale, again, indicator of that motion. So therefore, H and E are both, yes, they are functions of temperature. Now, so based on this, if we define, I mean, we generally define differentials like dH and dE, so small amount of change of H and small amount of change in E. In general, these, when we do that, this can be represented, for example, the variation in H, which is dH, can be represented by a constant, which we call Cp, times the variation in temperature. Similarly, for E, internal energy, we say this is equal to a constant Cv times dt, okay? Okay, maybe I should correct myself here. Maybe I should not say constants for Cp and Cv. In reality, they are not constants. I mean, depending on the speed of the flow, they can be assumed to be constants, but in reality, and as you can, of course, mathematically expect from these equations here, Cp must, in reality, must be a function of temperature itself. Similarly, Cv also must be a function of temperature itself. The thing is, by the way, these have names. Cp is known as specific heat at constant pressure, constant P, let me say. And this one is specific heat at constant volume, Cp and Cv. And they have dimensions. Their dimensions are the same as the gas constant. So these are joules per kilogram Kelvin. Both of them have the same dimension. What does this mean in reality? It means that I don't know, if you take, let's say 1 kilogram of hydrogen, so H2, right? So this is another type of gas. 1 kilogram of hydrogen, and in order to change the temperature of 1 kilogram of hydrogen 1 Kelvin. So let's say you went to your chemistry store on the highway. You said, I need 1 kilogram of hydrogen. You got it, and then you say, okay, I'm not happy with this. I just want to heat it up. So if you want to change, or in order to change its temperature 1 Kelvin, you have to spend this many joules of energy. That's the physical interpretation of Cp and Cv, specific heat at constant pressure, specific heat at constant volume, meaning that if you do that process, what is the process? Heating up or trying to increase the temperature 1 Kelvin, that's the process. I don't know how you can do it. I don't care how you do it. If you can just do it, you have to spend this many joules of energy. But if you do that process under constant pressure environment, you have to spend a certain amount of energy, which is the numerical value of Cp. But if you do the same process under constant volume, you have to spend a different amount of energy. So that's what we physically mean by Cp and Cv. Specific heats at constant pressure and volume, and these can be used actually through these equations to determine the H and the E values. Now, in general, this is how it works. But let's say in a more applied sense, for moderate temperatures, so let's say we say that Cp and Cv are functions of temperature. Of course, for moderate temperatures, meaning that not very high temperatures, so maybe I can say temperatures less than 1000 Kelvin, okay, for moderate temperatures, meaning that temperatures, let's say approximately less than 1000 Kelvin, okay. In that case, Cp and Cv are they still are functions of temperature, but the change, you can find that those functions they are available in different books. But if you calculate, let's say, the change in Cp compared, for example, if you're at 500 operating at 500 Kelvin, and then you know somehow you wanted to go up to 700 Kelvin, change in Cp is going to be very minimal. Same arguments are true also for Cv. So for temperature and for environments or ambients that are, let's say, moderately at moderately high temperatures, less than 1000 Kelvin, changes in Cp and Cv are almost negligible. So they can be assumed to be in reality constants. So for moderate temperatures like T less than 1000 Kelvin, let's say Cp and Cv are, let's say, more or less constants. Okay, so which I mean that they can be assumed to be not dependent on temperature. That's what I'm trying to say. So if Cp and Cv are constants in these equations, then I can integrate these equations and I can say H becomes equal to Cp times T, and E will be equal to Cv times temperature. Okay. Now, the question is, for a high-speed flying aircraft, is this the case? Okay. Well, let's say for up to some, first of all, in terms of airflow, in terms of temperature variations with altitude, yes, temperatures will be way below than 1000 Kelvin. Well, as you accelerate the what we call total temperature, and we will learn what that is, because when we talk about now compressible flow and high-speed flying vehicles, we have to distinguish between what we call static temperature and total temperature, which is also known as the stagnation temperature. We will learn what they are. But stagnation temperature, whatever that is, it includes some kinetic energy information, the flight speed information. So therefore, it can start going higher than 1000 Kelvin. So if that is the case, you know, as your speed increases to higher and higher and higher Mach numbers, maybe this may not be valid. So you have to be careful there. Okay. If there's you know, you're talking about you know, 2000 3000 Kelvin temperatures, you cannot use these equations. You have to go to these equations and find out the CP dependence on temperature, find out that equation, use that to calculate the actual value of CP. Another example I would like to make is related to aircraft engines. In aircraft engines, of course, we do have very high temperatures because of the fact that we have combustion. Basically, we inject fuel, we burn it. At the end of the combustion chamber, we can just very easily go beyond 1000 Kelvin. So generally, in aircraft engine calculations, we do not like to assume CP and CV as constants. Okay, so we need to calculate their actual values. So in propulsion classes, you will probably learn that. But for a large number of, let's say, compressible flow problems that are of interest to us in the context of this class, temperatures are moderate, so we can treat these as constants. By the way, if this is the case where CP and CV can be assumed as constants, and therefore H becomes equal to CPT and E becomes equal to CV times T. If this is the case, we call this a calorically perfect gas. Okay. So we initially defined perfect gas, started talking about it yesterday. But now, under these conditions, if this is also holding, if these conditions are also true, now we call it a calorically perfect gas by definition. So what else? Let me check my notes. So yeah, as we talked about, for example, yesterday, just to cover my notes, atmospheric re-entry, right? If you're from a space vehicle re-entering Earth's atmosphere, getting exposed to extremely high temperatures. So in those cases, specific heats also are not constant. So good. So now another maybe reminder for you from thermodynamics is that these specific heat values, Cp and Cv, actually are related to the gas constant as well. Okay, so the gas constant R, as we defined it in the perfect gas equation, gas constant R is actually the difference between Cp and Cv is equal to Cp minus Cv. Okay, so if I just repeat what I described regarding Cp and Cv, Cp, amount of energy that you spent to raise the temperature of a gas for 1 Kelvin to 1 kilogram of that gas. To raise it 1 Kelvin, you need to spend so much of energy, and that process happening at constant pressure. similar process happening at constant volume, you spend a different amount of energy to do the same thing, Same thing is to raise the temperature of that gas, 1 kilogram of that gas, 1 Kelvin. You spend a different amount of energy. Well, the difference between them is actually equal to what we know as the gas constant. If we generally manipulate this equation a little bit. If we divide both sides with Cp, so it becomes equal to, let's say, divide both sides with Cp, then I can say R over Cp becomes equal to 1 minus Cv, looks like a G, Cv over Cp, okay, Cv over Cp. Now here we also introduce a new definition as well. The ratio of these two specific heat values, Cp to Cv, is we generally use the Greek letter gamma to designate this, and this is known as the specific heat ratio, okay, gamma. And we can actually make use of gamma here in these equations. Then this becomes equal to the upper equation here becomes equal to 1 minus 1 over gamma is equal to R over Cp. So I can manipulate from here and I can write Cp. So specific heat at constant pressure in reality is equal to gamma times R after manipulating this, divided by gamma minus 1, okay? And you can do a similar exercise and obtain an expression for Cv, and that becomes equal to R over gamma minus 1, okay? R over gamma minus 1. So Cp, this is how basically these are related. Now this the value for gamma for standard atmospheric conditions for air. So let's write it down. For standard conditions or let me put it this way, for air at standard conditions, generally gamma is equal to 1.4, okay? So which means that Cp, specific heat at constant pressure, is about 40% higher than Cv. So that's what we mean, because it's equal to their ratio. And just to remind you, R is equal to 287, okay? And so that's 287 joules per kilogram Kelvin. Gamma does not have a unit, as you might imagine. It's just a ratio of two specific heats, so there's no unit. The value of Cp, again, for air at standard conditions is 1005 joules per kilogram Kelvin, okay? And therefore, the value of Cv for air at standard conditions will be basically, I don't remember off the top of my head, but it's going to be equal to 1005 minus 287. So it's going to be around what? If somebody can do this for me, my brain has stopped in the afternoon. Joules per kilogram Kelvin. Okay. Let me do that quickly for you. You are not helping.
977.
Cannot be 900.
Oh, sorry, I forgot my.
Siz de yorulmuşsunuz, sırf ben değil.
Hocam hesap makinesine basmayı unutmuşum tuşa. 718 hocam.
Evet, 708, tamamdır. Teşekkürler. 718. 718 joules per kilogram Kelvin is the value for CV at standard for standard air conditions. Onur, teşekkürler sana da, Melih sana da. So these are typical numbers. Why am I writing these numbers? Well, we're going to use them a lot in our upcoming equations. For example, when we are dealing with shock waves, normal shock waves, oblique shock waves, expansion waves, so high-speed aerodynamics, you will use a lot of these. I strongly suggest you know, it's not relevant that I suggest you will deal with these so much that you will memorize them by heart anyway. Any aerodynamics person should know these by heart. Good. So basically, after covering these gas properties, we will also make a little reminder of some of the concepts of thermodynamics. And I know that you have taken the thermodynamics class. So we're just going to review some of the, remember some of the concepts. Of course, the first one will be the first law of thermodynamics. Okay. So basically, first law of thermodynamics is, I mean, to put it very in a short summary, it's basically what we call the conservation of energy equation. Okay, conservation of energy. When I say conservation of energy, I am conserving the energy of what? Right, that's the question. Am I conserving the energy of an apple, an orange? What am I conserving the energy of? Well, the answer is a conservation of energy of a fluid particle. Okay, so sometimes we call it a system as well. So to keep it generalized, if in fluid mechanics, it's the conservation of energy of a fluid particle, but in the thermodynamic process sense, it's the conservation of energy of a system. So if I designate that system, let's say this block here is a system, and it can be moving or not. It does have a boundary, as you can see. So there is a boundary involved that is separating whatever is inside from the outside. So we call this a system. This system is interacting with its surroundings. So, you know, there is a boundary separating whatever is inside from the outside. Outside we call surroundings. Okay. Now, this system can, while it's interacting with its surroundings, okay, or let me put it this way, the question is, well, how does it interact with surroundings? This interaction occurs in two ways. First of all, it occurs through what we call heat transfer. So there could be some heat going in or out. So let's say a small amount of heat can be going in or out. So how can heat go in or out? You know, somebody you know, puts it in the oven, and the hot air. I mean, initially it's, let's say, cold meal, and then the air inside the oven is hot. So there, of course, because of the temperature difference, there will be some heat transfer from the higher temperature to the lower temperature. So this is some kind of interaction. The second type of interaction, is related to work. Okay, so it can also be both ways. So a small amount of work, let's say delta W, which means that what is work? I mean, work is not related to heat transfer. Work is something else. It means that, I mean, it could happen both ways, meaning the system here can be doing work on surroundings, or the surroundings can do work on the system. So what does that even mean? Okay, But it means, for example, this. I mean, just a simple example. Let's say this little blob here is moving, in a gas, and for whatever reason, this blob wanted to get larger, wanted to get bigger and bigger. So how can, so, sometime later, it wanted to go to a state, it's going to be, let's say, much larger than its original state. Then, in order to do that, that blob has to push its surrounding, right? It has to push its surrounding away, whatever it has at its surroundings. Let me clean up this funny picture here. It has to push its surrounding away so that it can get bigger, because it wants to increase volume. It wants to occupy more space. So while the surrounding says, it says to its surrounding, look, I want to expand. I want to get bigger. And surrounding says, okay, you can do that, but it's not for free. You have to pay for it. Then what it says, what do I have to pay for it? Well, you have to spend some energy. It's not for free, sorry. If you want to spend some energy, you can go get bigger. So it does that. So it spends some energy to get bigger and pushes its surroundings, and it gets bigger. Amount of energy that it spent to do that, we say it actually did that much of work. Well, the opposite of this story can also happen. And for whatever crazy reason, the surrounding can decide, okay, look, system, you will have to get smaller. You are occupying too much volume, you are going to get smaller. And the system is going to resist to that. And the surrounding is going to say, okay, and if you resist, I will have to spend some energy, and then I will crush you, basically. I will make you smaller. Then in order to do that, there has to be some energy spent to do that by the surroundings. So that's what we say surrounding is doing energy on the system. So that's also work interaction. So whatever we do, both of these cases, delta Q and delta W, if there is some work interaction going on between the system and surroundings, or there's some heat transfer going on between the system and surroundings, that changes the energy level inside the system. Okay, maybe I should say, to be proper, dE. So that's the energy change inside. So the change of the internal energy of the system. Okay, when it's doing all these interactions with the surroundings, getting heat, giving out heat, or pushing surroundings away, or surrounding is pushing it to get smaller. All these interactions cause a change in the internal energy level of the system, dE. So that is balanced. So whatever interaction that is occurring in terms of heat transfer or in terms of work will be equal to the change in the internal energy level of the system. If you are, let's say, adding heat, so if this is, let me use a different color. If you are adding heat, so the arrow is this way, surroundings is, let's say, at a higher temperature, heat is being added into the system. Of course, I mean, you are heating it up, what do you expect? It's going to get higher energy level, right? So dE will increase. And at the same time, if there's some work happening, meaning that if for example, if the surrounding is doing some work on the system, meaning surrounding is pushing the system to get smaller and smaller, well, what will happen is it will push the system, so it will get smaller, but when it gets smaller, there's going to be little volume. Little volume means there's going to be less space for the molecules to move around, and then it will increase its basically pressure and temperature levels. So that will change its internal energy as well. So generally, if the work is done on the system, we say that is positive work, and if heat is added to the system, that is we call positive heat addition, and therefore the balance of it we call dE. So we are saying that the energy level of the whatever substance is inside these boundaries, and our substance is at this stage air, for example, the energy level of air I can say fluid particle in general, the energy level of the fluid particle is going to be changing. Of course, we know that different types of energy exists. If it's not moving, it's basically internal energy. But if it's also moving, I mean, the system or this blob can be moving as well with some velocity. If it's moving, it also will have a kinetic energy. When it's exposed to these delta Q or delta W interactions, its kinetic energy will also change. So if it's let's say, heavy fluid like water, it's for example, its potential energy will also change. So when we say TE, to keep things generalized, meaning to keep also moving emotion in picture, so this we call the total energy level. So it contains internal energy, it contains kinetic energy, it contains potential energy. So if there are other energy types, you can add it to this list. So that's what we call is the first law of thermodynamics, the energy conservation of the system. We have some definitions related to the first law. The definition is called an adiabatic process. Adiabatic process. Okay. This is defined as if there is no heat is added or taken away from the system, taken away from the system. So basically what we're trying to say is this delta Q over there is zero. So that's what we're trying to say. We call this by definition an adiabatic process. Okay, good. Now, let's see. Okay. We have two more definitions. Okay, let me discuss them and we will stop for today. But these two definitions that I'm going to discuss now are more related in reality to the second law of thermodynamics, which we'll probably have time now to discuss next week. But the first one is what we call, the definition is what we call a reversible process. So you might remember from your thermodynamics classes. Now, a reversible process means that, I mean, this process is, when we say process, it could be any process that is occurring in nature, or it could be any process that's occurring in your engineering system, right? And for your aircraft engine, or it could be just a river flowing, any process in nature. If there is no, what we call dissipative phenomenon occurring, okay, then we call it a reversible process. So first of all, what do we mean by dissipative phenomenon? So dissipative phenomena is basically friction. I can say right out of the bat. It's friction. So we know that in any physical process, you might imagine, okay, any physical process, we always have friction. We always have friction. What is the bad thing about friction? Well, it unfortunately causes energy loss. For example, let's say you're just let's say, very simple example, you have, let's say, a plate and you have a block on top of it, okay, and you are trying to push that to the right. We know that there is some friction here. So the problem is you will be spending all this energy to actually get this block moving and keep it moving towards right. If you stop pushing it, maybe it will slide a little bit, then it will stop. So, I mean, what is causing it to stop? Because normally it shouldn't stop. You have already spent all that energy to move it. Well, unfortunately, the bad news is the friction ate up all your energy. It drained all the work, all the energy, your all energy input to the block, and it drained all of it, and nothing is left, so it's not moving. Sorry. Okay, so all the energy and all the effort you spent is basically got dissipated. It got dissipated to temperature increase in the surface in the interface between the block and the plate, and it's gone. Energy is turned to. It just helps increasing the temperature of the surface a little bit. It's not useful anymore to be used for pushing this block. So that's dissipative phenomena friction. In fluid mechanics or in aerodynamics, that occurs through viscosity. Okay, so viscous phenomena, effects of viscosity, or in heat transfer conductivity, or in like chemical engineering, mass diffusion, those are all dissipative phenomena. They cause reduction of useful energy. Well, let's say for some reason you ignore that. You say, okay, I'm going to ignore the dissipative phenomena that's happening. I'm going to act like there's no friction, or I'm going to act like there are no viscous effects. So we call it inviscid flow, right? So then what happens is thermodynamically, the process, whatever it is, actually can be reversed, meaning that if there is no loss of useful energy, that process can be reversed theoretically. So that's the fundamental definition of a reversible process. That's kind of an idealization, of course. By the way, in real life, there are no reversible processes. You can generate some processes that can get close to being reversible, but this is kind of an idealized process. And how do we quantify? Let's say a process is not reversible. By the way, we call it irreversible. Then the thing is, can I actually quantify how irreversible it is? Well, we do that quantification through what we call the second law of thermodynamics, okay? Through the definition of entropy. But before we go there, final definition, and we are finishing up the class, is that if a process is both adiabatic, so delta Q is 0, and reversible, we do have a special name for it. We call it the isentropic process, okay? Isentropic process, which means that this is both adiabatic and reversible process. And as the name suggests, this means that, this means isoentropy. This comes from that word, and iso means the same entropy. So it means that it's a process where entropy is not changing. Okay, so whatever entropy is, so let's say S is entropy, or delta S entropy change, let's say, will be equal to 0. So that's what we mean. So it means if delta S is equal to 0, we call it an isentropic process, and it happens if a process is both adiabatic and reversible. So next week we will start from now the concept of entropy. So talk about the second law of thermodynamics. Now we will revise that as well. Okay. So let's stop here. Let me stop recording. And if you have any questions, we can discuss now. Otherwise, I will see you next Wednesday.